Hello everyone. Today we will try to write a code just to explore some steps in multidimensional scaling. Okay, we won't try too many configurations. We will just try a few configurations because this way we are trying to understand how the algorithm actually works. Okay, so we will try a few configurations and we will see what is the best among those. Okay, so just a quick recap. In multidimensional scaling, what we do is we try to create a smaller dimensional representation of the original data. Okay, so here we will try that for iris data. So we know we will ignore the species variable as of now. So we know we have four variables. So the four individual, and suppose we want to get a one dimensional representation only. Okay, we don't even want a two dimensional representation. We want a one dimensional representation. So first we will consider the first four individual variables, and next we will consider PC1, PC2, PC3, PC4, and out of these 8 configurations we will choose the best configuration. Okay, so let us try. So my D is iris with species column removed. This is my data. For each configuration I have to store stress, so let me create a blank vector for storing stress, and let me get the distance matrix delta. So delta is original distance matrix, four-dimensional data based on four-dimensional data. So dist d method diagonal, and I want this to be okay. Actually, I don't need repeated values. So what we can do is we can convert this into a vector. Let us see if it works. If I can convert it to a vector, class of delta is still a distance matrix. So C, okay, so this is numeric now, and let me just head of delta. Okay, these are some of the distances, and length of delta will confirm 11175. Should I get these many distances? How many distances should I get? I have 150 observations. Okay, and I don't want diagonal entries. Okay, so from 150 cross 150, first I will subtract the diagonal entries and then divided by 2. Divided by 2. Correct? I have those many entries. Okay. So either the lower diagonal or the upper diagonal, because of the symmetry, anyone is okay with me. So we have got exactly those many entries. And now I have to try various configurations, and for each configuration we will construct a D matrix, that is the lower dimensional distance matrix, and then we will fit a regression model with that lower dimensional distance matrix as the response and this original delta matrix as the regressor, and then we'll compute stress for every model. Okay, so let us first try the four variables. So for I in 1 to 4, so suppose the lower dimensional representation is just ith vector of data, so di, okay, and then I have to construct a distance matrix based on this di, which I'll be calling as dmat. So d or ddist is, again I will make it a numeric vector, so dist of t. Okay, dist of t. Let us see if it works for I equal to 1. T is dist of I, and let us see length of d dist. It should match length of d dist. Correct. So we have to now fit a regression model. So lm with ddist as response and original distance delta as regressor. Okay, and let us see what happens. So these are the coefficients we get and summary of L. So r square is 0.58, not bad because we have only 5-dimensional data. Sorry, 4-dimensional data actually. So what we will store? We will store beta naught, beta 1 and r square, and of course the stress. Okay. So in addition to stress, let me have a matrix to store beta. So beta mat is a matrix with 2 columns, and I want to try 8 basically configurations. So 8 rows, and then I have to store r square also. So r square is another blank vector. Okay, so L dollar coefficients I will store in beta mat ith row. Okay, ith row of beta mat. Okay, my spelling of beta mat is incorrect. Yeah. And then r square. So r square at I equal to summary of L dollar. I think it is adj dot r dot square, but let us try. So s dollar, yes, adjusted r squared. And stress at I is, it is square root of summation of actual values minus fitted values whole square divided by sum of fitted values whole square. Okay, so stress at I will, so I need fitted values first. So F equal to fitted of L. Okay, so stress will be actual values. So actual values of the response. So d dist minus F whole square. Then we take sum of this square, divide that by sum of fitted value square, so sum of f square, and we have to take square root of the whole thing. Okay, square root of the whole thing. Okay, so let us run this for the 4 original variables and then we'll run this for the 4 PCs. Okay. Okay, let's see what do we get. So these are the stress values. So lowest value is for the third variable. Okay, and these are the r square values. You can see the r square value is highest for the third variable. What is third variable in the iris data? Petal length. Okay, and if I remember correctly, I think petal length has the highest variation. Yes, 3.11. Okay, so even in the PCA, petal length turns out to be the most useful variable. Okay, let me print beta. Okay, so you can see here petal length has the coordinate, sorry, the coefficient close to 1. Okay, okay, so let me try PCs also. So PCs we will store, so suppose PC is print comp of D scores equal to true and core equal to false because we want based on covariance matrix. And actually I just want to store scores. I don't want anything else. So dimension of PC we will check. 150 cross 4. So this is a score matrix. What we'll do is we will repeat this thing but with now the score matrix. Okay. So for I in 1 to 4, T is now PCI, ith column of the score matrix. And now I have to store this thing at 5th, 6th positions, etc. So 4 plus I, 4 plus I, because first 4 entries are corresponding to the first 4 variables. So I will store this at 5th, 6th, 7th and 8th position. Okay, let us see now what are my stress values. Okay, so you can see PC1 score is even further lower, of course slightly lower than the petal width score, and R square will accordingly be high. R square is slightly higher, okay, 0.98. So this shows that at least if I consider these, PC1 turns out to be the best, okay, best possible ordination in the current scenario. I can try PC with covariance matrix, okay. So we can try those 4. So I could have this as 12 and PC2 could be with correlation equal to true, and then dimension of PC2, and here I will have PC2, and this will be 8 plus I. Okay, we can still see that PCA based on covariance matrix still gives me the best possible stress value. Okay. So this is how MDS works, and then we can have that lower dimensional data as an input for self-organizing maps, and we can construct the clusters. Okay, let me stop here. Thank you.